Hello everyone, my name is TECK. So our IoT case study title is Public Restroom Availability Monitor. So I'm responsible for taking Part 3 implementation and analysis, Part 4 critical analysis and feature work, and Part 5 conclusion in my case study report. So in this presentation, I will present the implementation and data analysis and live demonstration, critical analysis and feature work, and last conclusion. First, we come to implementation part. So let's start with the network topology in the figure given. So when designing this in Cisco packet tracer, we don't just want to connect random wire. We want to simulate a real-world building environment. So we organize the network into four logical zones, such as store zone, main entrance zone, IT room zone, and janitor room zones. So first, at the bottom, we have the store zone. We have three store zones in our topology. This represents the physical toilet cubicle. This is where the edge sensing happen using the toggle button and LEDs. Then in the center, we have the main entrance zone. So this is the hallway outside the restroom. It houses the central MCU and the LCD screen to guide user before they enter the restroom. The user can check the status of restroom before they enter the restroom. Then at the top left is the IT room. So this represents the building server crosshair. It houses the home gateway, and the IoT registration server. So this is the brain that store the data. And then at the top right is the janitor room zone. So this represents the management office where staff use tablet or smartphone to monitor the status remotely. Now we move to the live demonstration. So for live demonstration, I will switch to Cisco Packet Tracer to demonstrate the system live. Now I will start to do a live demonstration in Cisco Packet Tracer. So let's start it. So currently, the system now is in default or IDLE state. As you can see at the store zone, store 1, store 2, and store 3, all the green LED are light up. This shows that all stores are empty now. Now we move to the main entrance zone. So this is the central LCD screen. It displays S1F, S2F, and S3F. So this S1 stands for store 1, store 2, and store 3, and F stand for free, which is mean available or empty. So this LCD screen can give a user a quick summary that all stores are available and let the user know the status now. So now let's simulate the user enter store 1. So I will toggle the push button. So in the real world, this represents that user now is enter and lock the door. So in the simulation, this toggle push button is simulate this thing, and then it represents the magnetic sensor detecting the door locking. So now I will start to toggle push button at store 1. Sorry. So now you can see the green LED is turned off and red LED turned on. So this provides the visual feedback at the store in front of user. So at the center, you also can see the central LCD screen. Now the store 1, the output is changes. So it changed from F to O. So this O stands for occupied. So this proves our edge processing logic is working in real time. So to understand the logic behind this, now we move to the MCU programming tab. So you can see the programming code is using JavaScript and it is event driven. So now I will extend the log. So this is the detail log. So you can see previously the system is in the default state or IDLE state. All the status of store are available. Now when I press the button, it will update, so you can see store one status change, and then store one status from available to occupy status. So the action, the green LED is turned to red LED. So this log is important for maintenance team to troubleshoot sensor issue. Now we move to the another part. So this is the IT room zone and janitor room zone. So I will move to the remote monitoring term. So you can see the home gateway and MCU is connect wirelessly, and then the home gateway is connect physically to IoT registration server. First we go to the IoT registration server. So first we need to configure the IP address, and then for the service we need to open the IoT registration, the IoT service. So this username and password is that when user log in to the dashboard using smartphone or tablet, and then it sign in, there will record in this tab. So remember first the server the server IP, because later we will access the web browser using this IP address. Now we go to smartphone, and then we click web browser, and then we type the server IP to log in. So you can see it go in the login page. So you can log in or sign up the account. So I will choose login. So you can see this is the web dashboard. So in the dashboard, store 1 is in occupied status, while store 2 and store 3 still remain available status. So this proves that our JavaScript code successfully translated the raw binary signal into human readable text. And then we also can test other store. For example, we can test store 2 and store 3. We press the button. So you can see the green LED is turned to red LED. And then we can see the LCD screen also update the MCU programming. So you can see the log, store 2 status change, and store 3 status change. Now we see to the web browser. So in web browser, it also changed the status of store 2 and store 3. It changed from available state to occupied state. Now we reset back. So for example, the user is finished and unlock the door and go out. So we can check in the dashboard. So you can see the dashboard also update simultaneously. So this means that the system can handle multiple input simultaneously without latency. So when the user leaves and unlock the door, the system automatically reset to available state and ready for the next cycle. So you can see in the log. So all are in the available state now. So that's all for my live demonstration. Thank you. After see the live demonstration, so let's go to the sample data presentation part. So the data generate two type of data. First, on the left of the picture is white dashboard. So this is where our code does the heavy lifting. The system translates a low binary signal, low or high, into human readable status like available or occupied on the dashboard. This ensures that non-technical cleaning staff can understand the status instantly. Then on the right of the picture, this is the serial log output. So you can see this is the backend log that generated by the MCU. So these logs are critical for verification. They give us timestamp history of every event. For example, we can track when a signal changes from low to high and confirm that the red LED turned on at the same time. Therefore, these two types of data can help us to confirm that the hardware action and synchronize perfectly with the network data sent to the cloud. Now we move to the data-driven decision making. So in this part, they have three decision making in different terms. First, user traffic optimization. This is for general public. So due to LCD screen data, user can make decision before enter the public restroom. They don't need to crowd the hallway or knock on door. This can reduce congestion and awareness. Second, resource allocation. This is for the cleaning staff. Instead of cleaning on a fixed schedule, the cleaning staff can look at the dashboard data. If the data show the restroom is in peak usage, they know that there's the time to stay away. If it shows the available status after a peak hour, that is the optimal time to clean. Third, maintenance alerting. This is for maintenance team. So the serial console log provide anomaly detection. If the data show that the store one has been occupied for 3 hours straight, we know that that is impossible. So this can alert us that either the sensor is broken or a user might be in difficulties. So this can allow us to take action proactively. So for challenge and limitation, there have three limitations in this part. First, technical limitation, single sensor modality. So our design relied on the door lock. So this may create two potential errors, such as false available and false occupied. False available means that if a user enter but forget to lock the door, the system thinks that the store is empty. Second, false occupied means that if a person lock the door and throw out underneath, the system thinks that the store is full forever. Second, connectivity reliance. So the remote dashboard is reliant on the Wi-Fi gateway. So if the Wi-Fi fail, the remote monitoring also goes fail. But the luckily thing is that the local LED will continue to work because they are controlled locally by the MCU. So this is our design strength. Third, non-technical barrier. So the installation is complexity in tile restroom. It is difficult. Although the components like MCU, LEDs, and sensor are not very expensive, but the retrofitting need wiring into wall and installing sensor on the door frame. So when in building with dozens of restroom or even more, the labor cost for installation will also be higher. Now we move to the scalability and security strategy. First, for scalability, we cannot just copy and paste the current setup to manage thousands of stores in a large airport. We need to move from HTTP to MQTT protocol for mass deployment. This can allow us to use specific topics like mode 1, floor 1, man, store 1 to organize data efficiently without clogging the network. However, putting a restroom on the internet also brings some security risk. If a hacker access the network, they could spoof the data and set all stores to occupied status. This can cause congestion and chaos. So to prevent this situation happen, our security solution include using WPA2 or WPA3 for encryption for Wi-Fi, TSL, SSL encryption for data transmission, So this can ensure that the data cannot be intercepted or altered by unauthorized party. Now we come to future enhancement. So to address the limitation just mentioned above, there are also three enhancements for the future version of our system. First, multimodal sensor fusion. So to solve the forced occupancy issue, where a person lock a door and leave, we will integrate PIO sensor with door sensor inside the store. The logic will be updated so that the status is occupied only if the door is locked and motion is detected inside. Second, predictive analytics. Currently, our system show only real-time status. So in the future, we want to use the store historical data to predict trends. For example, if the data show that the restroom are busiest at 1 p.m. to 6 p.m., so that then the system can automatically assign schedule for cleaning staff for other time. So this can optimize the resource allocation for staff. Third, scalability due MQTT. So to extend our project from one restroom to a massive airport, we cannot simply rely on point-to-point connection. We need to use MQTT protocol. So by achieving MQTT specific topic like uh, building one level 2 store, we can manage thousands of stores on a single server efficiently without clogging the network bandwidth. So now we move to the last part, conclusion. So first, we have achieved a successful proof of concept. We validate a complete end-to-end IoT architecture that capture physical action at the toilet stall and transmit the data to the cloud in real time. Second, we have enhanced user experience. So by provide a visual guideline, we solve the issue of privacy and hygiene. So user not longer to touch the dirty door handle or knock on door just to check availability. Third, we improve operational efficiency. So we prove that the facility management from transform from reactive cleaning to data-driven decision, where the staff only need to deploy when it is necessary. And finally, we validate our robust architecture. Our testing proved that the IoT cloud collaboration is work perfectly. So by processing data locally at the MCU, the system ensure that reliability and even during network unstable situation. So that's all for my presentation part. Thank you.